this is a robot arm I coded to play chess completely by itself. And this is a chess Grandmaster, one of the best players in the world, about to be beaten by it. How did we get here? Well, hold tight because this gets crazy. So, first of all, the big question. How the heck did I get my hands on one of these? Well, it all started when the guys over at Elephant Robotics, a Chinese robotics company, contacted me for a collab. They offered to sponsor a video with a robot of my choice, to make a project of my choice, and afterwards I get to keep the robot. Of course, I was absolutely thrilled, it was the deal of my life. Now, I already had some experience with mobile-based robots, and at the time I couldn't think of a cool project to do with one of those, so I decided to go with the myCobot robotic arm. I came up with a few ideas for what I could do with it, and mark my words, I do intend to do them all eventually, but for this collab I would turn it into a chess player. But I wouldn't just settle with making it play chess, oh no, I would turn it into a player so insanely skilled that no human could ever beat it, not even the world's top Grandmasters. However, I had a choice to make, because they offered 4 different flavors of the myCobot 280, with 280 standing for its 280mm working radius, basically depending on the way you control it. There's the myCobot 280 Arduino, which as its name suggests is meant to be controlled with an Arduino. There's the myCobot M5, which as far as I know is a more user-friendly version which can be programmed with simple apps and drag and drop. The myCobot Pi, which doesn't require an external computer to code it, because it has a good old Raspberry Pi inside, with its own Linux environment with ROS and whatnot. And finally, the myCobot Jetson Nano version, which is like the Pi version, but with a Jetson Nano instead. Now, of course, if I was gonna make an AI integrated robot, I'd need an SBC and not a microcontroller. But that left me with a choice between the Jetson Nano and the Raspberry Pi. And I didn't really break my head over the decision. The Jetson Nano was basically designed to run AIs and computer vision, which I'd need, while the Raspberry Pi is more general purpose and slower for this task, so I just went with the former. So I sent them my choice, and shortly after, 2 much anticipated packages arrived at my door, one containing the robot, and the other one containing the flexible gripper and USB camera flange which I'd need for my purpose. Although the arm itself already came with a camera, so now I have 2. Well, I'm not gonna complain. And the way you install hardware on the arm is quite interesting, because it has actual Lego holes at the end where you can plug in these actual Lego pieces. Now, if you've ever used them, you know they can get a bit aggressive, but the customizability it offers is really cool, and I'm pretty sure you could technically build anything out of Lego and turn it into the arm's tool. Anyway, I attached the camera, which has these same holes, and at 1 megapixel is almost as good as the camera I used to record myself. Ouch. And then inserted some more Lego pieces onto its holes to then attach the flexible gripper. And after having researched a ton about grippers for my own robot and making several prototypes myself, I just want to take a moment to appreciate the amazing technology behind this thing. The shape of the flexible gripper isn't just for looks. It's actually a mechanism that uses the Finbury effect, which is apparently registered as a trademark. And, well, just see how it works for yourself. It can wrap around objects it grabs without using any joints whatsoever. I'm telling you, fingers are so overrated. Anyway, with that out of the way, it was onto my physical setup. I had done some calculations about the size of the board, keeping in mind the robot's operating radius and the size of its base, and settled on a 21 by 21 cm board, separated 3 cm from the robot's base. I designed it on Canva with my custom colors, which both contrast well with the black and white pieces, something that would be extremely important for the robot to reliably read the state of the board, and kinda make it look like a chess.com board. So I cut that printed on special paper, and as the base, took this nice wooden board from my basement. I then made the measurements, glued the chessboard, and screwed the arm's base onto the board, and my basic physical setup was complete. I'd need a bit more of a user interface later on, but at this point, I just couldn't wait to start coding my new gadget. Booting up the arm for the first time is actually surprisingly easy. You just plug in its power supply cable, connect a keyboard and mouse to it, and wire it to a monitor using the included HDMI cable. However, my monitor was broken, so I decided to connect to the desktop through VNC like I do with my robot, although the arm has an Ethernet port, so I was worried it wouldn't have Wi-Fi. Luckily, that wasn't the case, as I found out when I connected it to my TV through HDMI. But it was really weird because it seemed to create a kind of Wi-Fi network of its own which other devices could connect to. I tried to scan the QR code, which was supposed to include the instructions for the arm, and it led nowhere, so I was forced to figure it out by myself by fiddling around with it. Turns out that Wi-Fi the arm created is a hotspot which, when you connect your PC to it, is precisely meant to allow you to connect to the arm through VNC or SSH without even having to connect it to your local Wi-Fi network. And it even had VNC set up already. Although it does mean that whatever you connect to the arm loses access to the internet, so I connected it to my home Wi-Fi instead and took it back to my room. The next part wasn't that smooth though, because with X11 VNC, the one the arm used, the only thing smaller than my budget for coming up with jokes about small things was the screen size. Classic headless problem. I fixed that by setting the resolution with a timed job at startup, but never actually managed to make the VNC work properly. Maybe my real VNC viewer wasn't completely compatible, but it would sometimes just kick me out of the session. However, this happened rarely enough for me to not bother dealing with it. If it did happen, I just restarted the VNC server through SSH. With that out of the way though, I was welcomed by a pretty complete desktop. I opened this myBlockly app, and it turned out to be a block code editor to control the arm. It also had this drop-down panel which allowed me to read and set each joint's angle, and it worked right out of the box. It was really cool to see the arm moving for the first time. There was also this other myStudio app, which apparently was supposed to be a kind of central hub for all of the robot's apps and tools. Although it didn't let me connect to the arm's serial port, most apps were completely empty, and the few apps it did seem to have just opened a browser window to an empty GitHub repo. As I had to find out myself due to the non-working manual, and as they later confirmed to me, this app is really meant to be installed on your PC to control the microcontroller versions of myCobot, and in my case was only useful if I wanted to flash firmware into the Atom, that microcontroller at the end of the arm with the LED matrix, which as far as I know is in charge of the inverse kinematics and joint control. Although that already came flashed, so yeah. All that didn't really matter anyway, because the main tool I'd used to make the software for my robot would be VS Code, as you can also control the joints programmatically using the simple and handy myCobot module. And here's where we get to the juicy part, the code. Because here's the problem. When you look at a chessboard, you can pretty easily tell that there's a pawn there, a rook there, a queen over there, which color they are, and if a player moves a piece, you can tell what they're doing. But how do you teach all that to a robot? This might sound more straightforward at first than it actually is, because I ended up having to tackle problems at basically every step of the process. For starters, how do you tell the robot what, out of everything it's seeing through the camera, is a square of the board? For this, while waiting for the arm to arrive, I had thought of using a warp matrix, which, as its name suggests, is a matrix describing how you warp an image, like those document scanners do. This turns the board the robot is looking at from an angle into a 2D square, as if it was looking at it exactly from the top. And if you get the size right, when you divide that resulting image into an 8x8 grid, each square in that grid will be a square in the board. That's easy enough, but it's not much use if the robot can't tell what it's looking at, because to play chess, you need to know where there are pieces, what color they are, and what type they are. And for a human, this is fairly easy, but the robot's just seeing meaningless blobs of black and white on a green background. Now, let's ignore the piece type for now. There would be two main ways to detect if there's a piece on any given square or not. You can either train a convolutional neural network, a kind of AI, with hundreds of images of occupied versus unoccupied squares, combining the different colors and telling it which are occupied and which are not, until it learns to distinguish between them, and this is what's called a YOLO, or you only look once model. Or you can say, if everything's green, there's no piece. If there's black or white, there's a piece. And this is called color thresholding. Now, of course, the first option was way too much unnecessary effort, especially if the other one could work just as well. So I decided on color thresholding, and I already had in mind exactly which module I would use. OpenCV, the undisputed king of computer vision in Python, which also happens to support warp matrices. But now, the elephant in the room. How do we tell a pawn apart from a bishop if they're both just round black blobs? Well, perhaps the easy way would be to make them more than black blobs. If you color each piece differently, the color thresholder would be able to tell both if there's a piece and what type it is based on its color. Although that would remove the distinction between black and white, so perhaps you could leave the normal colors and maybe add a colored dot on top of each piece. But come on, what kind of kindergarten chess set is this? No, if I was gonna make a chess playing robot, I would make it work with any normal set of black and white pieces. How? Well, I came up with a much cooler and smarter way to go about this. You see, the board always starts off in the same way, with the rooks in the corners, then the knights, then the bishops, then the king and queen, and a row of pawns in front of them. And this means that, at the start of the game, you know exactly which piece is which. But then say you move a piece. If the robot can only detect occupancy, it'll just see a square which was occupied before and is now unoccupied, and a square which was unoccupied before and is now occupied. Therefore, we should be able to infer that the human moved a piece from the now empty square to the newly filled square. And even though a single move doesn't tell you the state of the whole board, it's easier from here, as there happens to be a module called Python Chess, which can create and hold a board object and update it with the moves you give it. And you can then pass that to your chess engine. More on that later. Except this, by itself, will not work, because what if you capture a piece? All you'll see in this case is one square becoming empty, and you have no idea where that piece is now, because it may have replaced the square of any other opponent piece in its range. Also, what about castling, where the king and rook interact in a completely non-standard way? Or en passant, where a pawn is captured despite not being at the destination square? Or what about promotions? Because, in case you didn't know, when your pawn reaches the other side of the board, it can promote to a queen, but also to a rook, a bishop, or a knight. Well, to solve all of this, I came up with the following. For every move the human makes, Python Chess computes all the possible legal moves they could have made given the state of the board before the move, and then, when the robot looks at the board, if any one of those moves matches the occupancy map it's saying, we know exactly which move has been made. And this will work for all the special moves like castling and en passant, because what we care about is the end state. As for promotion, I decided to add some buttons so the player can choose which piece to promote to. So the vision part was definitely possible. Now on to the fun part, the chess playing brain. If you've ever played chess but had no one to play against, you'll know you can play against a bot instead. And behind each bot, there's a chess engine, which is the program that actually knows how to play chess. Now, there are a bunch of chess engines. Some older, some newer, some better, some worse. But for more than 7 years now, the undisputed king of chess engines has been Stockfish. Stockfish is a huge project, and I could make a whole video about how it works internally, but I'll try to make it short and simple this time. You see, chess engines work by producing a search tree, where each branch is a future possibility for the current state of the game, and the branches for those branches are the possible futures for those states. This can go on for many layers, eventually producing an insane number of nodes. Then, engines use an evaluator to determine which, out of all those possibilities, would be the best. Really, so far this is what any human player would do, though with much further foresight. But of course, such a big tree would be useless if it was too big to handle. So Stockfish is able to analyze millions or even billions of these nodes every second, thanks to tons of optimizations, both big and small, made by its hundreds of contributors over time. One big way it's able to do this is its search method, alpha-beta searching, which itself is an optimization to the famous minimax algorithm. Again, I won't go into the nitty-gritty, but it basically looks for the possibility that offers the highest minimum advantage and lowest maximum disadvantage in the worst case scenario for each future. Also, while other models, especially older ones, use the handcrafted evaluator to assess positions, with a ton of manually inserted rules and heuristics, Stockfish uses what's called an efficiently updatable neural network, or NNUE, go figure, which uses interconnected layers of neurons with different weights that produce a final output value given an input board, and whose weights, as its name suggests, can be quickly updated when the state of the board changes. Anyway, all in all, thanks to this incredibly optimized brute force process, Stockfish currently stands at an ELO rating, a system used to assess the skill of chess players, of 3,644, and it just keeps increasing. For reference, the highest ELO ever achieved by a human being in history was 2,882 by Magnus Carlsen, who would have a 25% probability to beat someone just 200 ELO points above him, and a less than 0.4% chance to beat someone, or, well, something, 800 points above. In other words, we don't stand a chance. Alright, so now that the robot has looked at the board, and we've passed the state of the board to Stockfish, we need the robot to move its piece. Now, ideally, what you do is get the coordinates in space of the corners of the board, and then map from there to each individual square on the go. However, there was this really annoying non-linearity to the coordinates, and the inverse kinematics calculations kept failing, especially for points further away, which was also really annoying because they don't tell you why they fail, they don't even raise an error. So this meant I had to manually move the arm, either physically or by fine-tuning the joint angles, to each and every one of the 64 squares, to record the joint angles for each one and write them down in this huge array which took me like 2 whole days to make. But anyway, with all of this in mind and a clear plan, I began coding. Naturally, I started with the vision system, and the first thing I needed was the warp matrix. So I chose some joint angles which left the arm looking roughly down at the board, and started by giving OpenCV's very conveniently existent find chessboard corners function a try. However, this turns out to get the inner corners and meant I had to do some extrapolation, so instead I went with a simpler approach where I just clicked on the 4 outer corners myself and computed the matrix from that. Once I had the matrix, I made my main code. And let me give you a quick rundown because I think it's really cool. First we have the imports, for some general modules, by myCobot, OpenCV and the chess stuff. Then we have a little playing flag, the aforementioned warp matrix, the joint angles array, an offset function in case I recalibrated them, and a dictionary to translate from files, which someone decided to name with letters, to column indices. Next is the myCobot initialization. After that, I initialize all the GPIO pins I use, you'll see why there are so many shortly, and I also initialize the chess engine by pointing to the Stockfish 17.1 file I downloaded. Next, we have our functions. The first one, which I called OccupancyBoard, takes our virtual board object and turns it into an occupancy grid like the one our camera will be producing, to make the comparison I talked about before. And here's an interesting one, the look at chessboard function. It starts by sending the specific angles I chose and opening the gripper so it doesn't cover the camera, and then takes 10 pictures with a small delay, doing the following with each one. First, it rotates at 90 degrees counterclockwise, which wouldn't really be necessary but it makes things much easier to work with, and then applies the warp matrix I had calculated to turn the capture from that perspective into a 400 by 400 pixel square I can work with. Then, it turns the color format for the picture, which originally is in BGR with specific blue, green and red values for each pixel, into HSV, which uses hue, saturation and value instead, as this is actually better for color thresholding. I also create an elliptical kernel, which will basically just be the shape of the grains I'll later use to degrain the picture. And now's the time to analyze each square's occupancy. So I divide the 400 by 400 square into 64 50 by 50 squares, but then I only take the 30 by 30 square in the middle, leaving some margin. This is because when I tried to use the whole 50 by 50 square, parts of some tall pieces would leak into nearby squares and cause false positives, and this simple fix turned out to work amazingly well. After that, I apply a filter to get only the black and white of the actual pieces by creating a mask spanning a fairly big range of color, which will select the whole background, and then inverting it. Don't worry, we're getting there. I then degreen the picture, deleting stray pixels and filling in small holes with the little kernels from before. Finally, if more than 20% of the 900 pixels in our 30 by 30 square are piece pixels, we declare that square as occupied and add the result to this sample's occupancy grid, building it by repeating the same process for all 64 squares. And once we have our occupancy grid, we move on to the next sample, and once we have 10 samples, we stack and sum them, and declare the squares detected as occupied by more than 6 samples as actually occupied. And with this, we get our final occupancy grid. The last function is the one for the give up button, to flip the playing flag to false if you press it, and end the game at any point. And the first thing in the main part of the code is actually starting a thread to run this listener in the background. And once that's running, our robot is ready to play, so it'll play a sound file to tell you
ready to play. Press start game to begin.
Now, before, I had to use WAV files because I only knew about Pi Audio, but I discovered this other module, PlaySound 3, which is much more straightforward and supports MP3 files. Although, unfortunately, even though it said in the datasheet the ARM had a speaker, mine didn't, so I had to get a little USB speaker for it. But anyway, then the program hangs, waiting for you to press Start Game, at which point a new board object is created and Stockfish is properly configured, because you can actually decide how powerful you want it to be, and in fact you can set the specific ELO you want it to reach. Now, it would have been really cool to set this with a potentiometer, so you could set any value you wanted as the ELO, but the Jetson Nano doesn't support analog input, and even though the Atom does, that function is not exposed in the firmware the ARM uses, so I was out of luck for that. Instead, I bought this big old rotary switch with 12 positions, one of which turned out to not work, and assigned a value from 1320, which forgot to mention is the minimum and probably already beats the vast majority of the world's population, to 3190, and then a maximum. I configure Stockfish for 2 threads, so it can use 2 of the Jetson Nano's 4 CPU cores, 256 MB of hash, which is the RAM I'll allow it to use, limit strength to true, and the ELO to the corresponding value. Well, except in the maximum position, where I set limit strength to false, and Stockfish just plays as formidably as it can, with no ELO limit. Then, the robot waits for you to make the first move and press the Move Made button. I didn't want to have it be a boring old standard button like the rest, so I ordered this huge heck of a push button instead, which electrically is probably overkill, but at least it'll look cool. And once you do, it'll look at the board, and for every legal move in the previous state of the board, occupancy it, and compare it with the occupancy grid the robot is seeing. If they match, it adds that move to a list and keeps going. When all legal moves have been compared, if this list contains one matching move, that's our move. If it contains exactly 4, we check if those moves are promotions, and if they are, the robot prompts the user to press either the Queen, Rook, Bishop or Knight button to select which piece they're promoting their pawn to. However, if there are multiple matches and they're not promotions, an ambiguity has happened. They are rare, and at first I expected my new method to fix them, but I realized that if a piece could capture multiple other pieces by simply replacing them, the board would look the same in the end in all cases. If this happens, which again is not often, partly because the thing's so good it barely even lets you take its pieces, the robot reads the possible matches and you press the button when you hear the move you've made. And for this I went full local and synthesized a sound file for every single square in the board.
I couldn't tell what move you made. Press the big button if you did. G5, 2, H7.
So once we've got the human's move, we push it to the board object and it's time for Stockfish to respond. To do this, we use the engine.play function, passing our board object, giving it a limit so it stops at a search depth of 30 moves or after 5 seconds, whichever arrives first, and setting ponder to true so it can keep thinking in the background afterwards, predicting the opponent's next move and planning how it'll respond to it. And then, after getting the origin and destination column and row that move corresponds to, we start to handle our possible cases. First of all, if it's a promotion, the robot will inform you of which piece it's chosen, so you can replace it accordingly if you have a spare piece. If it's a castling, it first moves the king accordingly, and then we have 2 possibilities: kingside or queenside castling. either the kings on g8, in which case the robot moves the rook to f8, or the kings on c8, in which case the robot moves the rook to d8. However, as you might have noticed from the sheer enormity of this code, I don't just send the joint angles when moving pieces. Instead, I calculate the coordinates that would correspond to those joint angles and first send the arm to a point a bit higher than that, so it'll approach them from the top most of the time. I say most of the time because, as I said, the inverse kinematics fail sometimes, and that's why I can't rely on this for the final position. Anyway, I then handled en passant, which is this weird movement I guess someone came up with out of boredom after getting tired of playing chess all day, which was pretty easy as the engine tells you when this is the case, by taking the pawn at the origin row and destination column. Then we have normal captures, where the robot will just take out the opponent piece before placing its own. And if none of this is the case, it just scraps its piece from the origin square by sending the angles corresponding to the origin row and column from my array, moves it to the destination square in the same way, and then slightly opens the gripper to release it without moving any other pieces. Most of the time. Then, we push that move Stockfish made to the virtual board, and the game continues until it ends or you give up, at which point it'll be game over, so the loop will exit and the robot will play a little sound file depending on who won. So, with the code done, I tested it on a temporary setup, it absolutely destroyed me, and I decided to make my little control panel. I started by making a button board with the start game, give up, and promotion piece buttons, using the same style and measurements I've used for my past controllers. I then designed a knob for my rotary switch, which I think looks pretty cool, and made this section for it where it tells you the elo each position corresponds to. Then, once the big button arrived, I took its measurements and made this third stage at the top for it. I combined it all into this cool case, added a hole for the cables to come out and two smaller holes for screws, broke it down into pieces with measures to be able to easily put it together later, and sent them over to my 3D printer. Up first was the base, and look at how insanely cleanly that fits. And then came out the button board, to which I attached my little buttons. However, for the rest of the parts, I realized you couldn't really see the text, especially since I'd printed some of it upside down to cut down on supports. I first tried to solve this by filling them with white glue, but it ended up turning transparent, so I panicked and marked it with correction fluid instead. It didn't turn out perfect, but it's readable. So I screwed the base onto my board, assembled the section with the small buttons and the one with the knob and the big button, put it all together, and wired it to my arm. And I will admit, like a third of the cables are G and D because I wasn't gonna bother making a common ground when I had just enough G and D pins for every button. I then glued on the speaker, tidied up the cables so they wouldn't be all over the place, trimmed the board a bit, and added some banding to it. Then I created a startup app to launch my script, which at first gave me some issues because the UART interface took up the THS1 serial port shortly after boot, and my robot was officially done. However, to test the actual prowess of my arm, I needed someone far more skilled than me. So I decided to look at the chess.com leaderboard for my country, Spain, and contacted the top few Grandmasters, inviting them to come over to play against my arm. No one seemed to read my message though, but then I got my only response, and it was actually from Álvaro Alonso Rosell, a Catalan player whose elo currently sits at 2,544, placing him as the 7th best player in Spain and 214th in the entire world. Although I did notice his rating is even better in the Blitz game mode, where he ranks 3rd in Spain and 109th in the world. Anyway, all of this goes to say, this guy is the real deal. I was honestly surprised as I live pretty darn far from Catalonia, but it turned out he had some travels planned near me and would be able to come. Of course, I was absolutely thrilled and eagerly waited for the moment. However, when relocating the arm to my living room, I ran into a problem. It suddenly became unable to distinguish occupied squares. Looking at the debug frame, I noticed it seemed to be correcting the image automatically, and thinking that might be the culprit, I disabled white-black correction, manually set the brightness, and it worked. Last minute save right there. And then finally, the big day arrived. Alvar rang at my doorbell, accompanied by two people who he introduced as his editor, Ramon, and one fear I had was the stereotype often associated with chess players of having complicated personalities. However, they were all so nice and very talkative. He told me a bit about his background, and it seems he's living the life. He goes around traveling and meeting other top players, and he even played against Magnus Carlsen. But anyway, shortly after, I switched on the robot, and he decided to give it a go at the lowest possible elo to get a sense of its playstyle. To my relief, the visual system worked like a charm, although you could see it wasn't fully accurate when being commanded positions. Still, it was enough for its task, and once Alvar was satisfied with his first taste of the robot, he gave up, which would be a very funny clip out of context.
Gave up already? Wanna try again?
And directly dialed it up to full unconstrained power. Alvar started his game with the Catalan opening, which he is famous for, and an intense battle followed in which he remarked the engine was quite aggressive.
Also, it's not just beating me like slowly, no. He's playing full on style here.
Yeah.
Yeah. Wow. Like I could teach this game to my students and they will learn quite a lot. Because he's using dynamic chess.
One by one, the robot started to take his pieces with no respect.
I guess. He doesn't have any respect for my position.
And shortly after, before anyone could realize, the robot had already put him into a dead end, and in a few moves had his king completely cornered. And just like that, it checkmated a world-class Grandmaster like it was nothing.
Oh man, he doesn't even give me the hand or something. Yeah. Oh my god. Wow, it feels so strange. Like it feels like I don't know. Like I couldn't believe it's that good, you know.
The Jetson Nano's fans hummed in satisfaction, and the ARM's quest to prove robot supremacy was complete. Also, what absolutely baffled me was that after the game, the dude just casually entered the entire thing, move by move, into his laptop by memory. You see, Alvar actually has a YouTube channel, and in fact it was his editor who kindly sent me the shots he took with his far superior camera and mics, where he'll be analyzing the game in detail. So if you like chess, do make sure to check it out. But wait, first I have an announcement to make. Because you see, even though I'm a tech nerd, I am also a writer. I've written a couple of books in Spanish, my native language, but I thought my second book, which talks a bit about life, the universe and everything, titled Alpha Omega, could be an interesting read for you guys. So I decided to translate the entire thing myself and published it on Amazon. So if you're interested, I'll leave the link to it down in the description. I hope you'll enjoy it. Anyway, thanks to Elephant Robotics for the arm, thanks to Alvar and Company for coming over, and thanks to you for watching. Make sure to like and subscribe if you haven't yet, and I'll see you guys in the next video.